Hi everyone, and welcome to this webinar, which is on structural optimization for a better future with Peregrine. By way of introduction, I'm Tom Pritchard. I'm the principal engineer here at Limit State, and I'm joined today by Matthew Gilbert, who is our managing director. Over the next 30 minutes, we'll provide you with an overview of how, when we're designing for the future with efficiency in mind, optimization is an increasingly important tool for structural engineers. More specifically, we'll be examining the way in which we're addressing this using our new plugin tool for Rhino, Grasshopper, Peregrine, using its parametric modeling environment. I'll pass over to Matthew shortly, but just as a brief contents, obviously we're going to look at the background, which is what Matthew will be talking about. He will then pass back over to me to run through a couple of example designs using Peregrine. Firstly, a relatively simple truss, and then moving on to a larger scale, more realistic stadium roof design. Then I'll talk a little bit about what's on the horizon for Peregrine, summarize, and then at the end of the 30 minutes, there should be a little time for questions. If you want to post them at any time, there's a questions box in the web interface, which you should hopefully have in front of you, and we can go through those towards the end. So without further ado, what I'll do is pass you over to Matthew, and he's going to talk about the drivers for efficient structural design and the background to Peregrine.
Thanks, Tom. If you just go to the next slide, please. Okay, so I'm going to just cover some familiar ground really initially. We're living in a climate emergency. It's very real. Organisations like the Institution of Structural Engineers in the UK have identified 6 steps to address this challenge. So low carbon, lean design, zero waste, influence to build. If we don't dress the metal, so to speak, then in the area of buildings, we've got huge problems. We're actually going to see a complete switch from operational carbon being the big driver to being embodied carbon. That's the carbon that's used to make the materials that are forming our constructions. So if we don't do anything, it's been estimated that 90% of carbon emissions associated with building will actually be embodied carbon in the period 2015 to 2050. So huge issue, huge challenge. Next slide, please. So a big question is, can we use optimization to achieve lean designs with lower embodied carbon? There have been lots of attempts to do this in recent years. Problem is that a lot of the tools that have been used are either inefficient, not very flexible, and also not very accessible. Often in-house tools have been employed. What we're proposing to do in our work here is use structural layout optimization to create widely accessible tools. Next slide, please. So what is structural layout optimization? It's actually an area that's been that has its history back well over 100 years, also referred to sometimes as for example, truss topology optimization. It's really the process of finding the most efficient structure from a wide range of possible arrangements, and we can tailor the optimization depending on the complexity of the problem that we're dealing with. So, for example, we can include Euler buckling and so forth in the formulation if need be. Next slide, please. If you're not familiar with layout optimization, then I would strongly recommend that you visit this site, www.layout.com. Basically, got a simple web app there. You can very, very quickly and easily change the loads and supports and see what effect that has on the optimized structure. Next slide, please. So, question is, can we embed layout optimization in tools that are already widely used in the construction sector? In particular, can we embed it in parametric modeling tools in order to realize significantly lower carbon designs? Next slide, please. And of course, our answer is yes. It comes in the form of Peregrine, which is obviously the subject of this webinar. developed in association with colleagues at Arup and University of Sheffield, and very, very powerful and flexible tool, particularly for use at the conceptual design stage. Next slide, please. So workflow-wise, it's a sort of linear workflow. You define the problem, optimize, post-process, and output. Next slide. In terms of problem definition, that means specifying where your loads and supports are, what the loading is, what materials you've got at your disposal. Optimization is tailoring the sophistication of the optimization you want to carry out. Again, for example, buckling, whether you want to include that or not. Next slide, please. And then once you've got an initial solution, there's various tools to refine that design, simplify it as you see fit, so it can be more useful for communicating the key features of the design to colleagues and so forth, and then clearly outputting that in whatever form is suitable. Next slide, please. So it's relatively early stages, but we've already seen Peregrine being used to design, for example, this structure on the left, the pipe support. So it was used to effectively initially sense check the conventional design, and then used to influence the revised design. And then on the right, another potential application is design for additive manufacture. We're involved in a large European project involving partners across Europe, including MX3D, who have fabricated this 2-meter tall cantilever structure, which is based on a Peregrine design. So I think this is really hopefully the tip of the iceberg, and hopefully we'll see much more wide range of uses of the software in due course. So I'll hand it back over to you, Tom, for the rest of the webinar.
Thanks, Matthew. And as mentioned, we're just going to go through a couple of brief examples to show the power of the Peregrine software and how it might be useful in your conceptual designs. So the first thing I need to do is we'll just introduce the first problem. So we've got a relatively straightforward, simply supported beam with point loading, and the questions that we're going to be asking ourselves are things like how much weight can we save compared to a conventional Warren truss design, what type of alternative structural forms are possible, can we ensure that the optimized structure is practical from a construction point of view, and how does the optimized form change with differing parameters. So what I'll do is I will just bring up Rhino, and we can see here that we've actually got the canvas with everything laid out in much the same way. I'll just move that out of the way for a second. As Matthew was describing, so at the top left here, we're designing the design domain geometry by adjusting the length and the height. We're also looking at things like the support, the loading, and then we have the optimization and post-processing, and then finally the visualization of everything. Alongside that, what I'm going to do is compare the volumes that we're getting and the designs that we're getting back to a more traditional Warren truss design. So that's the first thing that we're going to look at here. So if I zoom in to the left hand side, we can see our domain size is 4 by 20, so 4 meters by 20, with a central point load there. And the first thing that I want to do is say, okay, for a traditional Warren truss design, what is the manually derived volume or solution for this? And we have this at the bottom here. So if I just turn on the user-defined structure and preview that, bear with me. Change the loading to 6,000. Okay, so now we have a volume for traditional Warren Truss design, which essentially has the same size top elements in the top chord, same size bottom elements in the bottom chord, and the same size diagonals. We have a volume of 1.141 there. So first what we want to do is compare what we get for a traditional layout optimization alone. So if I then come up to here, we can see we have a layout optimization component. If I turn that on, it scrolls through and we can see here, actually we've got two solutions. First of all, on the left-hand side here, what's actually happening is essentially a size optimization of the elements as defined in the traditional Warren Truss. So going from having equal size top and bottom chord and diagonals to having different ones, so effectively being able to size each element individually. You can see already by doing that we're saving 24% of the volume. But on the right hand side here, we have much more freedom in the design domain for our layout optimization, and we can see that the complexity is controlled by the user setting above, where we have a number of nodal divisions here that feed into our design domain, but we have a much more complex structure with a volume that is now over a third lighter than the traditional Warren Truss. But obviously we can see that that particular type of structure is not necessarily practical in terms of construction. So what we want to do then is start to introduce different types of ways of simplifying the structure and seeing what the effect on the volume is from that. So that's what we can do in our post-processing here. At the moment we can see it's turned off, but we have a number of different stages. So I'll quickly just pass through all of them. So the first one we have is a geometry optimization, and essentially what that's doing is taking the nodal positions in this structure here and moving them until they are at a more efficient position. So it can merge nodes together and it can move them around until it finds a more optimum position. And from that, we have two other types of post-processing that we're going to look at here. Firstly is merging joints, and secondly, perhaps more interestingly, is simplification. And in the simplification, you can see we have a mode here, and we have three different options. Either we reduce the number of members overall in the structure, or we can reduce the number of members at the joints, or we can reduce the number of members at just the most complex joints. So in this particular case, that would be at the top center underneath that load. The mode that we've chosen, as we can see here, is mode 2, which is reducing the number of members at all the joints. And what happens within that is essentially it's doing a Heaviside formulation, and it's working out how much it can simplify that structure for a specified amount of volume increase. So here we've got a 5% volume increase as the limit on it, and it's going to say how much can I simplify that structure in the way that we've specified, and what is the outcome in terms of the structural form. So what I'm going to do is I'll go there and I'll turn on this post-processing, and you can see in the background that it's just working through. And now we have a number of different options for our design. So on the left-hand side here, again, we can see our original Warren Truss design, but if I move to the right, we have our size optimized one, we have our layout optimized one, and if I zoom in and maybe make that a little taller, we can see here we've got geometry optimization actually allows us to reduce the volume even further, so utilize less material, but that may still be slightly complex. So what we do is look at the simplified version. So we say simplify mode 2 and the geometry optimization afterwards, and for a very small increase in volume, we can see that actually we've got a much simpler and easier to fabricate structure as a result. And then finally, looking at the merged nodes, we can see that we have a different structure again, but again around a third or 33% volume saving over the original Warren Truss design by undertaking this optimization and the post-processing. So we have a number of different ways to post-process our optimized structure in order to make it more practical in the real world. And there are other ones such as filtering and the other simplification modes that we don't really have time to go into today, but are also available within the software. So now we have this. Let's see what happens if we change one of the parameters, say. So what I'm going to do is I'm going to change the height of the design domain. So if I move my way all the way to the left, we can see here our domain size. I'm just going to change that from 4 to 6. And we can see by changing the height from 4 to 6, we have different structural types with different forms and different amounts of volume saving. So whereas previously we were saving maybe 33%, here we can see that in our layout optimization and then our subsequent post-processing, we're saving somewhere between 27 and 17% of the volume over and above the one from the manual design. And the last thing here, just as an aside, is to see, and it's a bit of a nod towards the additive manufacture that Matthew was talking about earlier, is that we can also, if I turn off the preview of the normal design and zoom in a little, we can see here that actually we're using the multi-pipe functionality that's built into Grasshopper to smooth out the joints in our design in order to reduce the stress concentrations potentially. So that's the sort of thing that you can do using the output from Peregrine to feed into other functionality within the Rhino Grasshopper environment. So that's the first example. If I just switch back to the presentation for a second. So what did we learn from that design? Obviously, size optimization of the traditional design alone can save you a reasonable amount of material. So if you're going to do nothing else, then that is definitely worthwhile. But then if you want to take it those stages further, then layout optimization followed up with geometry optimization and the other post-processing functions within Peregrine provide you with a range of efficient but practical design options that you might not otherwise have identified by hand. And it's quick and easy to change the inputs to answer what if type questions. So what if the design domain was 6 meters high rather than 4 meters high? And that takes us on to the second example, which is one of design of a stadium roof. So something that's slightly more large scale and realistic. The questions we're asking ourselves here are, what does an efficient solution look like for this particular type of problem? And what happens when we consider effects such as gravity and Euler buckling? And how does the most efficient form change with differing parameters? So if we switch back in to Grasshopper again, I can't remember if I have, no, I don't, I need to open. The problem. So here we can see, actually I'll change the viewport to be perspective so that we can see that a little more easily. So here's our problem. We can see here that actually what we're doing is we're considering one wedge out of a number that make up this essentially circular or donut design for our stadium, and the red area there is the design domain. We can see, if I zoom in, we have line loading along one edge of it, and we also have supports which it's a little difficult to make out, but at the back there, one to prevent vertical movement, and then also normal supports along these two edge planes. And what we're going to do is we'll look at various different practical aspects that we can introduce into this design. So the first thing we need to do is actually just solve the problem. So if I come in, turn on the optimization, and we can see here that we have a structure with a volume of 4.49 times 10 to the 11. So that can be our sort of baseline. And What we're not doing currently is considering gravitational forces, and they're likely to play a very large part in this type of design. So the thing we can do is come into our material. We can see here we have a toggle for gravity that feeds into it. If I turn that to true, we can see what happens, and very quickly we've come up with an optimal solution where a lot of the material has been thrown to the outside of the structure, and we have essentially cantilevers working their way into the center, and that's what you may expect in this particular type of situation. If we then move our way back to just see what the volume of this is, we can see actually that it's essentially doubled by just by including those gravitational forces in there. But also, what about Euler buckling? Does that make any difference to the structure? We can turn that on and see how that then affects the outcome. And again, in the problem specifications here, we have an input which is allowing us to consider Euler buckling. Currently it's turned off. If I turn that to true, you can see software recalculates in the background, and actually it's probably quite subtle. So if I turn it off and back on again, what you'll see is these small elements here have disappeared, and these diagonals here have thickened up slightly, and the volume has increased a little bit, but not considerably from the previous one. So let's have a look now at what happens if we change the nodal density in the problem. Remember, the more nodes that we have in there is the more possible members in the optimized structure. So if we go here, we can see here at the moment we have 2. If I change that number to 12, for instance, let's see what effect that has on the structure. And as you might expect, the structure has become more complex because we've increased that nodal density. And similarly, the volume of material or the efficiency of the structure here has reduced down to 9.27, so we're using less steel work within it. And probably the last couple of changes I might want to make, let's have a look at the material properties. Let's see what happens when we change some of those. So we can see here we've got a tensile stress, and we also have a compression to tension ratio, which we've set currently to 1. If I say, okay, let's make the structure stronger in tension than it is in compression, so the C to T ratio of 0.5, and see what effect that has on the structure. And it took a little while to update, but we can see here actually it's made quite a difference to the outside. We've got quite an interesting arching sections within the 2 chords, and also it's adding more tensile elements in there in order to try and take advantage of that increased tensile stress limit. If we went the other way and say, oh, not 20 but 2, so now we're twice as strong in compression as we are in tension, possibly a sort of slightly more hypothetical situation, but one we might want to have a look at. We can see here that the optimized structure now is throwing in some compression rings, and the structural form is actually quite a lot different to the one that was previous. And as we're coming towards the end of the half hour, I think we should leave it there, go back to the presentation. If you do have questions whilst I'm summing up, now is probably a good time to start typing them. So what did we find out from the stadium roof design? So optimization and parametric conceptual design of large-scale structures is very straightforward and quick using Peregrine, and you can readily include real-world considerations such as gravity and Euler buckling, which actually, as we noticed in the first instance, have quite a large influence on some of the most efficient designs. So what's on the horizon for the software? So we'll be introducing a Peregrine Pro edition quite soon, which will be dealing with more holistic building design, including beam grillages. We'll be introducing tools for the design of cable-supported bridges, and we'll also be introducing components into it that allow us to consider global buckling as well as Euler buckling of the members. And to sum up, Peregrine for layout optimization is a powerful tool that you can use to rapidly identify highly efficient frame topologies. So ones that will save large amounts of material whilst also being relatively practical for manufacture. There are applications in both large-scale structural design and in additive manufacturing, and it's a valuable tool for conceptual design. And if you wanted to find out more information about the software, if you visit limitState.com/Peregrine, then there are details there for you. So we've got maybe a couple of minutes for one or two questions. So if anybody has one, then please feel free to ask now. If you bear with me, I will start looking as well, just to see if there are any.
We have a number, Tom. I think we can struggle to get through them all. I've just got one earlier one. Are these example files available to download? I think we can make these available, can't we, Tom, to participants of the
yes,
webinar?
certainly. They may take a little more time to just tidy up and get onto the website, but yes, we will make them available for people.
Can you speak more about holistic building design and what it entails and what it will include and what isn't now? Is a question. I mean, the big thing is actually allowing beam grillages. So if you imagine us in a multi-story building, we typically use beams or slabs for the floors, and then we have framing elements carrying primarily axial loading in the columns. So it's basically allowing both those two types of elements and then allowing them to be combined. And potentially, certainly we've seen some very interesting arrangements and some huge savings in material at the extremes, not necessarily practically usable concepts directly, but certainly adaptable and certainly features of those concepts that you could apply in practice.
Okay, thanks, Matthew. I'm conscious of the time. I'm also conscious that there are quite a few questions that have come in recently. What we'll do is we'll make sure that we go through all of those and respond to people after the webinar has finished, so in the next few days. Obviously, if you do have any more questions about the software or about structural optimization, then do feel free to get in touch with us. You can email us on info@limitState.com, and we're always more than happy to answer your questions. So I think that probably brings us to the end for today. I'd just like to say thanks to Matthew and thanks to everybody who has joined us today and asked all the questions. I look forward to answering them for you. And yeah, we look forward to seeing you again at one of our future webinars. Thanks very much.